Welcome, everyone. So my name is Mohammed El Kebir. I'm an assistant professor at UIUC, the University of Illinois, Urbana-Champaign. And today I'm going to talk about integer linear programming. So I'll be giving a brief tutorial, and you don't have to wait until the end. So let's make this interactive, okay? If there's any questions, just speak up. Well, this is a very busy slide. So what I do in the group is combinatorial optimization in computational biology. And the cool thing is a lot of problems in biology are discrete and combinatorial in nature. So what that means is, for instance, when we think about sequences, we're talking about strings. We're trying to find k-mers. We're trying to assemble sequences into a larger sequence. Phylogeny is basically just graph theory with lots of twists. And what this actually means is that a lot of our inverse problems correspond to really cool combinatorial optimization problems, where typically the objective function has to do with like this discrepancy between the object that we try to infer and the incomplete measurements that we have on that object, right? And that leads to a lot of really fun problems. Now, I'll skip this. When we think about problems, like what I'm going to be talking about today, are mostly optimization problems. So what that means is we have a large space of solutions. I'm going to call it pi of x. So x is an input instance, so x could be your data. And each solution has a score, okay? And when we do combinatorial optimization, we're trying to find one element in this space of feasible solutions that maximizes or minimizes some objective, okay? So this is FY star. And the other thing that we're going to talk about today are enumeration problems. So what if you want to enumerate the complete space of solutions, okay? Now, there's this discrepancy, this difference between problem and algorithm. So an algorithm, you guys know what an algorithm is, but I'm going to just belabor the point. It's a set of instructions to solve the problem. And we can quantify how good the algorithm is, either by looking at its running time, like is it a fast algorithm, is it a slow algorithm? And also we can think about, is this an exact algorithm? Is it guaranteed to give you the optimal solution? Or is it a heuristic? It comes with no guarantees. Now the interesting thing is, like many problems, a lot of problems in computational biology, they do not admit efficient algorithms, okay? So to say this a little bit more formally, a lot of problems in comp bio are NP hard. And what this actually means is that it's going to be really unlikely that you'll be able to find an exact algorithm that runs in polynomial time. And exact means it gives you the optimal solution, okay? What I'm going to talk about today is a technique that you can use in that setting. So if your problem instances are still small enough, and if you have a lot of constraints, you can still solve NP hard problems for practical problem sizes. So that's what we're going to be talking about today. And the technique is going to be, it's called integer linear programming. So I'll give you a brief introduction about the technique. We're going to do a little warm-up problem, and then I'm going to talk about two problems from my own research where we use ILP, okay? And these are slightly more advanced techniques, so let's see how far we get. But I think the focus is going to be on the first three bullets. So before talking about integer linear programming, I just want to talk about linear programming. So I hope you can see this box down here. So this is like the canonical linear program. So we have up here, we have the objective function, and this x is the variables that we're trying to identify. So c are coefficients. So when you look at this, so here's an example where x actually is a vector of two variables. So when you look at this objective function, it's a linear function, okay? So we just have the coefficients, they're constants, they're part of our problem instance. And then we have the constraints. The constraints are linear as well. So there are coefficients in front of every variable. They can be 0, they can be negative, they can be positive, but they're just constants. And we also have this right-hand side. So there's another constant there. And the variables have a domain, okay? So in linear programming, the canonical form, we just say that the variables have to be non-negative. So this is the exact same thing that I did over here in matrix form. And in the case of two variables, you can just plot the two variables on the plane, so x1 and x2, and you can think about constraints as like half planes, so they give you like a feasible region. So whenever you add a constraint, you kind of like cut apart away. So these 6 constraints over here, they correspond to these 6 half planes. And that's what you see over here. So this is the feasible region. And the objective function gives you a direction in which you want to optimize. So that's kind of like this dashed line. So it tells you want to optimize that way. And you can kind of like see over here, this is the optimal solution. So in linear programming, the optimal solution is a vertex of the convex hull. Okay? So it's kind of like a corner point. So that's linear programming. Now the cool thing is linear programming is very easy. So the formal term is it's in P. You can solve it in polynomial time. So there are exact algorithms that take polynomial time. And there's also this other algorithm, the simplex algorithm. Takes exponential time, but it's still used in practice a lot because it has really beautiful properties that you can use in branch and bound. Now, in terms of like solvers, there are commercial solvers, Cplex and Gurobi. I use Gurobi a lot. So these commercial solvers are actually, it's kind of sad, they're way better than the open source solvers. They're much faster. But you can get free academic licenses. Okay? And there is a bunch of open source solvers. So what I recommend doing, if you want to implement or use linear programming or integer linear programming, use a wrapper. So there are wrappers like Pyomo that will basically allow you to kind of like use either a commercial solver or fall back to an open source solver if the commercial solver is not available. So that way you can still distribute your packages and medical schools can use them or whatever institutes that can get an academic license. So the difference between linear programming and integer linear programming is this over here. So the domain of our variables changes. So in linear programming, it was greater or equal to 0, so it could be any fractional value. And in integer linear programming, this x has to be integer, has to be integral. So what it actually corresponds to is you get these so you get these points over here, these integer points. Those are our solutions. So just to summarize the point, so this constraint over here changes to this. That's the difference. But this difference makes everything hard. So in this case, the solution was over here. It was a corner point of the convex hull. And when you require integrality, the solution actually drops a little bit. Even though like this visual kind of like makes you think that it should be easy to like round and get like the nearest integer vertex, it's not that easy. So in fact, integer programming is NP hard. So you're not going to find a polynomial time algorithm that can solve this to guarantee to optimality, give you the optimal solutions. And the same solvers that I talked about, they support integer programming. Okay? And there's another caveat that I want to add here. You can also mix your variables. So a subset of your variables can be fractional or continuous, and the other subset can be integral. And a specific restricted case that we also see a lot in practice is where you require your variables to be binary, either 0 or 1. Okay? So I'm going to show you an example of a toy problem in a minute. But let's just talk about like how this is solved in practice. So I'll start with branch and bound, and then we'll talk about branch and cut. So the way you would solve, so we're talking about integer programming. So we have an integer program, and we want to solve this. And we're going to use a linear programming solver. We're going to call that linear programming solver multiple times. And the way you do it is you take your integer program, and you relax integrality. So instead of like saying that x has to be a natural number, you're going to say x has to be greater or equal to 0. It can be fractional. So you relax it. Okay? And then you solve the linear program. So what happens, so this is called an LP relaxation. So LP is linear programming relaxation. So we're minimizing over here. So when we change this constraint, we're kind of like making it harder. So what this actually means is that the LP relaxation is an easier problem to solve. So the feasible space is actually larger. You can kind of like see it over here. So this gray area, the feasible region, is a superset of like the solution space of the integer problem. So the LP relaxation, since we're minimizing, actually gives you a lower bound. So just keep that in mind. We're going to use that. So we solve this, and we get a solution. So let's call this solution x0. So there's two things that can happen. So either x0 is integral, meaning that x0 actually corresponds to integer variables, or like the values are integers, or they're not. So what happens in this case if x0 is integral? What does that mean? Any thoughts? Yes, I see people thumbs up. It means you're done, right? Because this LP relaxation gives you a lower bound, right? So it basically tells you that the optimal solution, cannot be better than what I find with this LP relaxation. And it turns out that the LP relaxation solution that you get is integral already. That means you're done in this case. If it's not integral, you have to do more work. And this is where the branching comes in. So what you do is you pick a variable in x naught, and you pick a variable. Typically, you pick something that is really fractional, that is as close as possible. So if this x was binary between 0 and 1, you would pick something that's close to 0.5, okay? Because that's kind of like where you have most uncertainty. You don't know if it's really 0 or 1. So I'm going to actually assume, it turns out I already assumed here that x is binary. So what you do is you branch on it. So you basically take a variable, and then you're going to explore all possible cases. So if we're looking at if this was binary, we would only enumerate 2 cases. So we would actually fix xi to be 0, and we also would fix xi to be 1. So these are the 2 branches that you get. So this is a different problem that you solve. And what you do is you do the same trick again. You're going to solve the LP relaxation. Okay? That will give you 2 additional solutions. And you keep on, branching. Okay? Yes?
So when you say it's binary, is that some additional hypothesis?
That's an addition. In this example, it turns out I assumed it was binary. But if it was integer, so typically what we have in practice is you would actually have an upper bound. So you can actually enumerate like all possible scenarios. But yes, yeah. But for this example, I want to make it binary so I can kind of like explain what's happening. Yeah. So this is like the branching part. But let's talk about the bounding. What does the bounding mean? So if at some point at this node, for instance, over here, this kth node, if we get an integer solution, what that actually means is we have a feasible solution, right? And that feasible solution will have a score. So that's this over here, right? So this C, so the coefficients times like the variables of x to the k, xk. And if that's actually better, if that's lower than this solution over here, which is not necessarily integral, what it actually means, because this is a low bound, it means you can actually prune this. Like whatever you're going to do in this subtree, you're going to add more constraints that will be worse than what you already had. So you can kind of like prune this part of the tree. So you don't have to explore that. So this is not going to be an exhaustive search. You can actually prune parts of the tree. The other thing that I want to add is you don't have to wait until you get an integral solution. When the LP relaxation actually gives you something that's integral, you can also take your fractional solution that you got and round it. So if the value is greater than 0.5 or greater or equal to 0.5, you make it 1, if we're talking about binary variables, or you round it down to 0, or you round it to the nearest integer in general. And if that solution is still feasible, satisfies all the constraints, that also gives you a feasible solution. And you can also use it as a bound to prune. So that's the bounding part. So the bounding allows you to prune. So I'm going to pause here a little. I'm hoping I'm kind of like making a general idea clear. Any specific questions?
Why is pruning adding more conditions, like constraints?
The pruning is not adding constraints. When we prune, what's happening with the pruning is we actually, at some point, we got a solution that is feasible. So it means 2 things. It's integer, okay? And it also satisfies all the constraints. So it's a valid solution to the original problem. It might not be optimal, but it is a feasible solution, okay? So we can actually evaluate the score of that solution and use it as a bound to prune other parts of the tree. So this is a feasible solution over here. And if this cost of that solution, so we're minimizing, if the cost of that solution is less than the cost of this solution, and this is not a feasible solution necessarily, so it does not have to meet integrality. If that's less, And because of this condition over here, you can prune. That's the bounding that's happening. Yeah. Yes?
How are you searching this tree? Are you, because, I mean, if you do a depth first search or something, then...
Yeah, there's a lot of heuristics and strategies that are, yes.
So that's a heuristic, then?
Yeah, yes, absolutely. And the way you search matters, as you're hinting at, absolutely, yeah. And also the variables in which you branch also matters. There's a lot of engineering that you can do to actually really squeeze out every last inch of performance. Okay, I think I need to speed up. I'll skip this branch and cut because I actually want to show examples. So we're going to do a warm-up problem. We're going to talk about clique. So we're given a graph, and we want to find a maximum clique. So this is a really hard problem. So maximum clique is a subset of vertices that are induce a fully connected subgraph. So in here, these three vertices form a maximum clique. You can actually also encode this as a maximum independent set problem. So what you do is you take this graph and you just flip the edges. When I say flip the edges, every non-edge, so there's no edge between V2 and V3, becomes an edge, and every original edge is deleted. So you get this complement graph. And an independent set is a subset of vertices. So in this case, V1, V3, and V4 form an independent set, meaning that there's no edge connecting any pair of vertices in that set. So that's an independent set. So the two problems are equivalent. And I'm going to be using maximum independent set to solve the max clique problem. And this is how you can do it. So we're going to use binary variables. So in this example, we're going to have a variable for each node. And it's going to be a binary variable. So 0 means you don't take it. 1 means you take the variable. Okay? And we're going to solve the independent set problem. So what this actually means is for every non-edge in the original graph or edge in the complement graph, you can only take one of the two nodes, right? And the way you can encode that is over here. So you would say x2 plus x3 is at most 1. Because if you would take both, they would both be 1, and that would be equal to 2. But you can only take 1. So that's why there's this at most 1, right? So that's how you can encode this problem. And you can kind of like do this for general graphs. Okay. So I'll show you real quick in a Jupyter notebook what it looks like. Just so you see what's happening over here. So this is the first toy problem that we had. So we just had these two constraints. I'm using Gurobi here. And we're just specifying that these are binary variables. Here we're specifying the objective function. And we're saying it's maximizing. And then you can solve. Okay, you just tell it optimize. And it will tell you, you can extract the solution. And it will tell you which vertices, which variables were actually set to 1 and which were set to 0. So that's how you get the solution. And you can do this. You can also encode this more general problem. So that's what I did over here. And I just want to show you. So this is a bigger graph. So I'm taking a graph with 125 nodes. This is the number of edges. And when you run the solver, so this takes about, on my laptop, I ran it earlier this morning, less than a second. And I just want to show you what's actually happening, because you can see the branch and bound happening. So here, this 0 corresponds to the root node. It's basically just doing the LP relaxation in the root node. And the reason why there's multiple zeros in there, it's doing branch and cut. It's adding additional constraints. I didn't talk about that, but there's like additional constraints being added. And at this point, it branched. Right? So it picked a variable and then it branched. And it's binary, so it actually has two subcases that it looked at. And it ended up exploring this many nodes in the branch and bound tree. So almost 2,000. And you get the solution. So it actually tells you there's a clique of size 34. Okay? And then the other thing that I want to show is, this is available on my homepage, so you can look at this notebook offline. When you change this argument, it actually becomes an LP relaxation. And when you solve that, you get a solution that has a higher objective value, 65, because it's a relaxed problem. And you can kind of like see it will cheat when it does that, because the variables can be between 0 and 1. So it's going to pick like this 0.5. Okay? So that's the first toy example. So it looks like I only have 9 minutes left. So I'm only going to do one more real example. So I'll be very quick. So this is from bulk DNA sequencing. So we're given bulk DNA sequencing samples from multiple regions of a tumor. We did variant calling, SNVs. So those are the columns over here. The rows correspond to the samples. And for each sample and SNV, we have the variant allele frequency. So that's the fraction of reads with the mutation. And what we're trying to do in this problem, we're trying to find a tree, deconvolve like these measurements, such that we can explain this frequency matrix as mixtures of the leaves. And these are the mixture proportions that you see over here. So that's the high-level idea of the problem. And I'm going to skip all this. So there's a lot of math that's happening. The only thing that I want to mention is, like in this paper, we actually show that this problem is equivalent to a graph problem. And in the graph, you can obtain this directed graph from the frequencies over here. So the nodes correspond to the columns. And there's a directed edge between two mutations if the frequency of the source mutation is greater or equal to the frequency of the child mutation, right? And solutions correspond to spanning trees in this graph. And these are not just any spanning tree. These have to be spanning trees that meet this additional condition, the sum condition, meaning that the frequency of the parent has to be greater or equal to the sum of the frequencies of the children. So I'm not going to explain why this is the case. Just trust me on this. It actually shows, we have a proof that shows that this is really the solution space. But we also show that this is really hard to solve. It's an NP-hard problem. But you can do this with integer linear programming. And what this actually corresponds to is a very simple ILP. So what we have is this variable x that tells you whether an edge is picked or not. So it's a binary variable, okay? And what we need to encode is we want this to be a spanning tree, okay? And we also want the spanning tree to satisfy the sum condition, right? So the frequency of the parent is greater or equal to the sum of the frequencies of the children. So this is how we do that. So to encode that this is a tree, there's two constraints. So there's one constraint that specifies there's got to be a unique root node. So there's only one, and we're indicating that with this variable r. So there's only one root node. And it also has to be a tree, meaning that every other node that is not a root node has an incoming edge. So that's basically what this is encoding over here. You can think about it. So either it's a root node or it must have an incoming edge. That's what this means. And this encodes the sum condition, like the frequency of the parent is, greater or equal to the frequencies of the children. So when you write this down, this is the number of binary variables and the number of constraints. And you can actually take this ILP, and I have examples of it over here, and just give this to Gurobi. And the cool thing that you can also do with Gurobi is you can use it to enumerate the solution space. You can tell it, give me all the optimal solutions. So if your ILP, if you have encoded it in such a way that there is a bijection between solutions of the ILP and solutions to your original problem, so you have to be very careful that there's no symmetries, then you can actually use your ILP to get the complete solution space. So that's actually what's happening over here. So there's this mode in Gurobi that gives you, so this search mode, when you set it to 2, it will enumerate solutions. And you can get all solutions of your problem that way. Okay? So there's a caveat here. Because we're solving NP-hard problems, don't expect this to scale to really large input instances. So that's something to keep in mind. But you can get a good intuition about your problem, and you can also use this to benchmark your heuristics. Any questions about this so far? Okay, good. So I want to do one more slightly complicated thing. So I want to talk about maximum likelihood inference. Like how can you do this? So this is going to be data likelihood. So our frequencies, the variant allele frequencies, they actually correspond to read counts, right? So this frequency of 0.8 corresponded to 8 variant reads and 10 total reads. So 8 over 10 is 0.8. If we had 80 over 100, that's also 0.8. But with 80 over 100, we're way more confident in 0.8 being a reliable frequency. If it was 8 over 10, if we did 7 over 10, that's 0.7. So there's a big difference. So you actually want to use you want to use a probability or a likelihood model that encodes for this uncertainty. And one way of doing that is you could use a binomial, right? So this binomial is parameterized by the depth, the number of reads that you sequence, and also the frequency f. And this frequency f is something that we don't want to, that we don't observe. We only observe A and D. And what the problem actually becomes is, given A and D, we want to find an f that maximizes this likelihood, but also meets like all the conditions that can be decomposed into a tree, right? So so f is not necessarily equal to A over D. So A over D might not give you a tree. So you actually want to find the closest f that gives you a tree, and closest is evaluated in terms of the likelihood, this binomial likelihood. So when you look at this binomial likelihood, so this f is a parameter. We don't have it anymore. We want to estimate that. D and A are constants. So when you look at this, when you squint at this, it's not linear anymore. So you actually have to think about ways to linearize this. And one really cool trick that you can use, so I'll just illustrate it over here, is you could do a piecewise linear approximation. So I'll show just the idea over here. So this is an example with like 5 variant reads, 10 total reads. So you can approximate this function using multiple pieces, okay? And as you increase the number of pieces, it's going to look more like the function in blue. And what you can do is you can actually take this piecewise linear approximation and plug it into your ILP. And this will allow you to simultaneously solve for the frequencies, which is this fractional variable, and also the tree. So you can actually linearize this whole model. But you can look at this over here in this notebook. I just want to give you a general idea of what you can do with ILP. So you can also solve more complicated nonlinear problems. The reason for the experts in the room, the reason why this works is because like we're maximizing and we're looking at a binomial, which is from the exponential family. So it's log concave. So yeah, we can actually exploit that here. Good. And then the final thing that I'll mention is sometimes your ILP could be too slow. And if you think about it carefully, you can typically find a class of constraints that make it really slow. So there's one thing that you can do. So I won't explain this problem, but if you have a class of constraints that make it really slow, you can actually remove those constraints, don't specify them. And what you can then do is you can actually run the solver on the slightly simpler problem, and it will give you a solution that is wrong. But that solution is wrong. You can actually tell it that the solution is wrong. You can tell it it's wrong because this constraint that I left out violates that solution that you gave me. So what you then do is you tell the solver, here's an additional constraint, go solve it again. So this is called cutting planes. And you can actually do this to speed up your solver by quite a bit. So that's what I'm showing you over here. So for this particular problem that I didn't explain, this is the percentage of constraints that we ended up generating. So it's less than 10 to the minus 4%. So 10 to the minus, a fraction of 10 to the minus 6 out of all possible constraints. And this actually allows you to speed up your, the ILP solver by a lot. For this problem, which corresponds to this paper, we really had to like pull out all these tricks to make it scale to practical problem instances. So the take-home message that I'm giving you here is sometimes like just plain vanilla ILP could be too slow, but don't give up. Like there are typically other tricks that you can do. And one of them is like this cutting planes that you can try to find. But in order to actually make this work, you need to have a very fast way of identifying violations. You want to have a polynomial time algorithm that gives you like this constraint is violated. So you don't want to spend too much time identifying the constraint that is violated. Yeah. Good, so I'll just stop here. I just gave you a crash course into simple topics and slightly more advanced topics. Thank you.